Okay, hello everybody. This is exam one from fall 2022 of MA 262. Yeah, not much to be said. Let's just get into it. Question one, we have this differential equation given to us. Biggest question to ask yourself when you're solving for one of these is, what method do I use, right? In this case, we're going to use separation of variables, and you might ask me how I know that. I know that because if I take a closer look at this differential equation, everything more or less is being added, or not added, sorry, multiplied or divided. Obviously you have your y multiplied with your dy dx. You have this 2x divided up here. And yeah, you have a little bit of subtraction going up top, but this at the end of the day is just a constant and not a variable, which makes it easy for us to say that this is going to be a separable differential equation. So let me rearrange some terms real quick. I'm going to divide the y over, which gives me something like this. And I'll rewrite this to make something easier to see here in a second. So we can also say that this is y squared minus 1 over y times 1 over 2x. And you'll see why I do that in a second, mostly just because now we have two very explicit terms consisting of our y's and consisting of our x's. So let me multiply the dx over. So I have dy is equal to y squared minus 1 over y times 1 over 2x dx. And then I'm just going to multiply, I'm going to divide this term over the left side. So I get y over y squared minus 1 dy equals 1 over 2x dx. Now we just integrate both sides. This top integral is a really standard, just u sub integral. If I let u equal to y squared minus 1, du dy is equal to 2y, and therefore 1/2 du is equal to y dy. And as we can see, we have a y dy up here and a y dy down there, so 1/2 du will just replace all of that. 1/2. So what do I get? I get 1/2 ln u, right? And using actually, no, I'll just keep it like this for now. And I'll tell you why I didn't add a plus c to the left-hand side in just a second. Let's integrate our right-hand side now. So you have 1/2 integral 1 over x dx. Pretty standard formula. That's just 1/2 ln of x. And I'm going to add this to the right side. And you really don't need a constant on both sides because they'll just kind of end up absorbing into another constant. Yeah. So now that we have this, I can set. Oh, but keep in mind our u was y squared minus 1, so really this becomes something like this. And now I have these two set equal to each other. Our 1/2s can cancel on both sides. And now I have this. So easiest way to get rid of the ln is to just raise both sides to e, right? Because when you have e to the ln of, let's say, a, you're just left with a. So e to the ln of y squared minus 1 is y squared minus 1. And e to the ln x plus c. Well, this is you have to be pretty familiar with this trick because it happens all the time when you're solving separable ODEs. E to the ln x is obviously, actually, I'll rewrite this. Multiplied by e to the c. This is the same thing, right? Using our exponent properties. I will continue my work up here. This is our same thing, but e to the c is just another constant, right? E is a constant, c is a constant. That just gives you another constant. What do you have? You have y squared minus 1. E to the ln x is just going to be x. And I'm going to call this new constant here, I'm just going to call it k. So you can effectively say this is kx. Y is equal to square root kx minus 1. So this is our like implicit solution. Keep in mind we do have this initial value here. Y of 1 is equal to 2. So when x is equal to 1, y is equal to 2. We're going to pretend I didn't do this right here. We don't need that right now. But when x is equal to 1, y is equal to 2. So 2 squared is 4, 4 minus 1 is 3. X is 1, k is equal to 3. So now you have y is equal to square root of 3x plus 1. So now we're asking, what is y of 4? Well, y of 4, you're just going to plug in 4 to x, you get y equal to square root of 13. And I get a. That's up there. Just double check that that's the right answer. Yes. Okay, so moving on to question 2. This is another ODE we have, except this time we use our integrating factor method. And as you can see, I have a couple of things written down, such as, so this is going to be the general form of any integrating factor question, and this is how we're going to find the integrating factor. One very important thing I want you to notice is that when we look at the general form of an integrating factor ODE, there is nothing attached to our dy dx. Here, something is attached to our dy dx. It's the x plus 1 attached to our y prime. So therefore, whenever you look at the question like this and you see that something is attached, you always want to divide it out. So the form becomes y prime plus 2 over x plus 1 y equals 2 over x plus 1 whole squared. And now, as you can see, everything lines up. Our p of x is now 2 over x plus 1. And integrating p of x is our first step to finding our integrating factor. Now, the integral of this is really simple. It's just 2 ln of x plus 1. And using our log properties, we can say that this is ln of x plus 1 squared. And you don't need these absolute value signs anymore since x plus 1 squared will always be positive. Now we're not done. Our integrating factor, as you can see, it's e raised to this. And as I mentioned earlier, e raised to the ln of anything is just going to be whatever is inside your ln, right? So our integrating factor equal to x plus 1 squared. So now, what do we do next, right? We actually take what we do next here. I'll move my work up here. Is we do y times our integrating factor, which is x plus 1 squared. And we take whatever is on the right-hand side. So our q of x function, we used to say this is equal to the integral of q of x times your integrating factor. Now, what is our q of x? Keep in mind, it's not 2 over x plus 1. It's actually 2 over x plus 1 squared because we divided out the x plus 1 to begin with. And as you see, when we multiply our integrating factor and q of x together, our x plus 1 squareds actually cancel, and we're just left with a nice 2 dx. So y, x plus 1 squared is equal to 2x plus c. And that's why I didn't add a c over here on the down at the integrating factor, because that would just be absorbed into this other constant on the right side. So now you have y is equal to 2x plus c all over x plus 1 squared. Right? Keep in mind, we do have an initial condition. So when x is 0, y is 1. So that equal to 1. X being 0 means you just get c. So c is equal to 1. And now you have your full solution. And now we want to find y of 1. So when, just plug in x equals 1. So y of 1 equals 2 times 1 is 2, plus 1 is 3. 1 plus 1 is 2. 2 squared is 4. So the answer you get is 3/4, which is the correct answer, and it matches the key. Okay, so that's 1 and 2. Now we have a tank problem. Before I do anything, I just want to write the general form we will be following all the time. R in times concentration in minus R out times concentration out. Now let's annotate this, right? So we initially contain 80 liters of a solution. So our initial volume is 80 liters. It's a constant. The solution, the 80 liters that is initially in here has 15 grams of chlorine in it. Now we're diluting the tank. So pure water is actually pumped in at a rate of 8 liters per minute. So obviously you can just tell that's our rate in. And the well-stirred mixture is pumped out at the same rate. So rate out is also 8. If x of t is the number of grams of chlorine in the tank at time t, find the number of grams of chlorine in the tank after 10 minutes. Really, this is just, you just have to set it up. This is mostly just a setup question. So our rate in, as you can see, is 15. But our concentration in is actually 0 because it's pure water. So this term automatically just kind of goes to 0. Now, what is our rate out? Our rate out is 8. And our concentration out, just a general form, is going to be x of t over v every time. It'll be x of t over v every time. Why is it that? It's because the mixture is uniform. So v we know is 80, right? So now our equation looks something like this. Because remember, there's a negative, and our minus r out is 8x over 80. We're going to simplify that down to this. So now we just have a nice separable ODE. We can say dx over x is equal to minus dt over 10. What do you get? You're getting ln of x equals minus t over 10 plus c. As I said, raise everything to the e again. So you're getting x is equal to e to the t over 10 plus c, right? But again, that'll become a new constant, right? This becomes a new constant. So really you have x is equal to ke to the minus t over 10. Yeah. So now this is our concentration, right? What's our initial condition? Our initial condition is that when the tank initially has 80 liters of volume, there's 15 grams of chlorine in there, which is essentially saying at t equals 0, we have 15 grams of chlorine. So again, x is our concentration, so 15 grams. So 15 is equal to t is 0, which means this you're raising e to the 0. E to the 0 is anything is 1. So k is equal to 15. So the solution of our ODE is x is equal to 15 e to the minus t by 10. And now we want to find the number of grams of chlorine in the tank after 10 minutes. So we just sub in t. We just sub in 10 for t. Get x is equal to 15 e to the minus 1, which you could rewrite as x is equal to 15 over e grams, which matches A. Yeah, I would definitely take time to be familiarized with these kinds of questions. I would recommend doing a kind of question such that this rate in times concentration in doesn't go to 0, because a lot of the time it actually won't go to 0. And you will most definitely see this, most probably definitely see this on exam 1. Okay, so number 4. Um, this is kind of a trickier question, if I say so myself. Let's just think about the ways we can go about this. So earlier, number 1, I mentioned how if it's separable, then anything that's being added together it has to be a constant. So you can divide and clean nicely and just get your x and y's on one side. However, we're adding and subtracting y's here. So you can kind of infer that it won't be a separable ODE. It's not integrating factor because there is no p of x function. The p of x is what's attached to your y, right? There is no y and there's no p of x function. You have a q of x, but there's no p of x. So it can't be integrating factor. Lastly, not lastly, but our last two options are Bernoulli's and exact. For Bernoulli's, like we know that on the right-hand side, there's like a q of x attached to a y to the n, and n is not equal to 0 or 1, right? Here, any y term is just any y is always raised to the first exponent. So we know it can't be Bernoulli's. So that really just leaves us with one option of exact. And you might be thinking like, oh, how do I get into this exact form? Well, the best way you can get into this is actually just cross multiply. So you have a 3x minus y, 3x minus y dx. Hold on, sorry. We're gonna do this first. X plus y dy is equal to 3x minus y dx. I'm going to move the dx over by subtracting it. And then I'm going to distribute my negative. This is what we're looking at right now. So one very thing to know. This is your m, this is your n. An exact equation is only exact if dm dy is equal to dn dx. Now here I know it's an exact equation, but I'll work it through anyway. Dm dy, anything with an x is going to be constant, so derivative of y is just 1. And dn dx, same thing, anything with a y will be constant, so derivative of x is just 1. 1 is equal to 1. Therefore, we know that this is an exact equation because this condition above holds true. That being said, our next step is just going to be, I'm going to list something out. We call this m and n just kind of placeholders, but our df dx is actually equal to x plus y, and our df dy, sorry, this is my bad. df dx is actually equal to y minus 3x, and df dy is equal to x plus y. X plus y. Okay, so now we have everything written out. Now we kind of just pick one and integrate. It doesn't really matter which one you do, just pick one, right? So we have, this is a multivariable equation. Your x's and y's are mixed together. F of x, y is equal to the integral of one of these. I'm just going to pick df dx. Actually, no, I'll pick df dy. No. Y minus 3x. dx, because that's, you always want these two to match, basically. This is a dx, so this will be a dx. That being said, let's integrate this. Remember, we're integrating with respect to x, so anything with a y is just going to stay constant. We're just going to add an x in front. This becomes this. Instead of adding a plus c, we're going to actually add another function called g of y. You'll see why in a second. Okay, that being said, now we take the partial derivative of this with respect to y because we have this g of y. We'll call this df dy is equal to x minus, this is a 0, because this is just all x's, plus g prime of y. What else is equal to df dy? This is equal to df dy. So as we can see, our x's match up, and we're left with g prime of y is equal to y. If g prime of y is equal to y, we can simply integrate both sides and get g of y is equal to 1/2 y squared. And now that is actually just your full answer if we just sub it in. So we have xy minus 3/2 x squared plus 1/2 y squared is equal to just c. And now from here, you can just say there'll be a couple negatives. They just multiply by 2, right? So, and the y squared is out front, so you have y squared plus 2xy minus 3x squared. 4 is e. Let me just double check that's the right answer. Yep, 4 is e. Okay, moving on. All right. So this is kind of just like a true false, glorified true false. Let's look at 1. We're saying the existence and uniqueness theorem for the first order linear differential equations guarantees that the solution to this initial value problem will exist in this interval -2 to 2. This is actually pretty easy to do. Once again, we want y prime by itself. So we're going to divide the x plus 1 over. So this becomes like, sine x on top times y plus cosine x all over x plus 1. Now, what are x values that cause discontinuities? We have x equals -1, 2, right? And our initial condition is y of 1 is 3. So that's another x value that we have to take into consideration. Now, keep in mind that the solution will exist in the interval, and there's a couple caveats for this interval. The interval cannot include any discontinuities, but it also has to include the initial condition. But -1 falls in between. -1 falls in between this interval. So our solution cannot exist in this interval because there would be a discontinuity at -1 for our differential equation, that is. So 1 can simply not be true. Let's look at 2. Y equals root x is a solution to y times dy dx equals 1/2. This is a really simple problem. Let's just find y prime first. That would just be 1 over 2 square root x. So y is equal to root x times 1 over 2 square root x. The root x's cancel, and you're just left with 1/2, which is exactly what 2 says. So we know 2 is true. And finally, dy dt plus 3y equals t squared y squared is a Bernoulli differential equation. This is very true. Why, you ask? Because I will show you in just 1 second. The classic setup for a Bernoulli equation looks something like this. The general form is the word I'm looking for. Y prime plus P of xy is equal to Q of x Q of xy to the n. And I mentioned earlier how n is not equal to 0 or 1. In this case, instead of x, this is just a t. That's just a variable they use. What do we notice? Our P of t is just 3. Our Q of t is just t squared. And our y of n is y squared, and n is equal to 2, which is not equal to 0 or 1. So therefore, we meet every criteria that a Bernoulli differential equation needs to satisfy. So 3 is also true, which makes our answer B. Okay, this is number 6. I've just wrote out a blueprint essentially for this question real quick. So obviously this is an exact solution or exact question because you have some equation multiplied by dx, some equation multiplied by dy. I've labeled our m and our n, and I've taken these two partial derivatives to show that they're equal to each other. Therefore, that this is truly an exact equation, just for, ease of mind, if you will. I've written out what our df dx is equal to, and I've written out what our df dy is equal to. And now, just as last time, let's start integrating. I will choose df dx just because I enjoy integrating with respect to x more than I do with y. Oops. Times sine y minus 2y sine x. And remember, we integrate with respect to dx. So once we take this integral, this stays as e to the x sine y. This becomes plus 2y cosine x minus x plus, again, gy. Now, don't forget, we do have to take this partial derivative with respect to y. So what does that give us? That gives us e to the x cosine y with respect to x minus respect to y, sorry. So that gives us plus 2 cosine x minus x is obviously just 0 with respect to y plus g prime of y. Now, so again, this essentially is equal to f of x, y. This is equal to df dy, right? Now, when we match our terms, we can see, oh, this is the same, this is the same. So we end up getting g prime of y is equal to 1. With a quick little integration, you get g of y is equal to y. Right? Not too bad. Now, so our solution with our c's is, I'll write this in a different color, e to the x cosine y plus 2, sorry, e to the x sine y plus 2y cosine x minus x plus y is equal to c. Now let's plug in our initial value, right? So y of 0 is equal to pi. So let's just plug in x equals 0. And that's when, y is pi. So e to the 0 is 1, sine of pi is -1. 2 times pi is 2 pi, and cosine of 0 is 1. Minus 0 plus pi. Therefore, we have C, right? And, hold on, sorry, sine of pi is 0. This is actually just 0. So C is just equal to 2 pi plus pi, which is equal to 3 pi. So, just discard these real quick. And then we can look at our signs. So we have a minus x plus y, which these both actually have, but the difference is here, and it's actually plus 2y cosine x. So our answer for 6 is D. Let me just double check that is the right answer. Yep, 6 is D. All right, moving on. This is a Bernoulli's because it follows the classic the uh, the classic form, which I will write down once again, just real quick, which is just dy dx plus p of x y equals q of x y to the n. Here n is equal to 2. And it can't be 0 or 1, as per usual. So we're given that b is equal to y to the minus 1. What we do from there is, if you look at the answer choices, everything is in terms of v's and x's. So what we do from there, essentially this is saying v of x is equal to y to the minus 1. So let's take this derivative with respect to x, right? We end up getting v prime equals minus y to the minus 2 times y prime, which this y prime is a result of chain rule, right? You're differentiating with respect to x, however, you have a y on the right-hand side. All right. So I'm going to rewrite this equation too, actually. I'm going to write this as y prime, just for continuity. Equals 3xy squared. Now, I'm going to isolate my y prime. So y prime is equal to 3xy squared minus 1 over x. Right. That's what this is. So, but if we take a closer look, we know that y prime is actually equal to v prime over minus y to the minus 2. Right. And then I will substitute that in there, v prime over minus y. Sorry, this is some bad algebra. I'm going to rewrite this. V prime equals y prime times minus 1 over y squared. So when I multiply that over, you get y prime equals minus v prime times y squared. Yes. So now you have the minus v prime y squared equals 3xy squared minus 1 over xy. That's what you have right now. That being said, now we just kind of do some algebra, to be honest. So you have minus v prime equals, I just put the negative over. This is what you're left with, essentially. When I distribute, I'm left with something like this. So b prime equals minus 3x plus 1 over xy. We don't, if you look at the answer choices, we have no y's at all, right? Oh, but what do we notice? Well, earlier on we say v is equal to 1 to the negative 1. There's a y to the negative 1 right right here, is attached to our 1 over x. So therefore we end up getting v prime equals minus 3x plus v over x. And once again, when I do a little bit of, manipulation, v prime minus v over x equals minus 3x, which leaves us with the answer of B, which is the right answer. So yeah, this is nothing but just a whole bunch of, like, one derivative and a bunch of algebraic manipulation, really. If it ever asks you to solve this, if you recognize now you have a ODE in terms of V's and X's, this is actually an integrating factor ODE. You solve for V and you plug back in what you substituted for. But that's not what this question is asking for. So number 8, which of the following alternatives list all stable equilibrium solutions to the differential equation? So first we want to find our critical points, right? Critical points is just when this is equal to 0. It's pretty easy. Y is equal to 0, 1, and 2. From here, we want to make our number line, or rather our sign chart, and try to make it like relatively accurate, like 0, 1, 2. And from here, we kind of just look at one thing. So if we have some y value greater than 2, what is the sign of our dy dx? Well, let's think about it, right? If y greater than 2, then everything up above is positive, right? Because, for example, 3 minus 2 is 1, 3 minus 1 is 2, and just 3. So positive times positive times positive, that's all positive, which means this arrow is going to point to the right when it comes to equilibrium solution. Now, what if y is greater than 1, but y is less than 2? Well, then it becomes a little stranger, right? Because if it's less than 2, then now our y minus 2 term, this becomes negative. This is still positive, and this is still positive. But when you multiply a positive, and a negative, you still get a negative. So now this arrow points to the left. What if y is greater than 0, but y is less than 1? Well, let's look at that as well. Um, if y is greater than 0, then this is still positive. But if it's less than 1, this becomes negative, this becomes negative. However, when you multiply a negative, and a positive, you get a positive number. So this arrow points to the right. Because we're looking for stable equilibrium solutions, we know 1 is a stable one, at least. Now we just have to check 0. What if just altogether y is less than 0? This one is pretty easy. These two stay as negative because, like minus 3 minus 1, minus 3 minus 2, those are both negative. But now this is also a negative. 3 negatives multiply together, make a negative number, which means this arrow points away from 0, making 0 unstable. Therefore, 1 is our only stable equilibrium solution. Means B is our answer. Okay, nearing the end of this exam now. Question 9. This is mostly just like a vocab question almost, so let's just get into it. I've written down some of like the criteria for REF and REF. So for both, all the row with all zeros need to be at the bottom. As you can see, that's the case in every example we get. And the pivot in each row starts to the right. So what I mean by that, for example, is like a pivot is obviously your first non-zero entry in your matrix. So if I had a matrix that was like 1, 0, 0, right? My pivot in the next row either has to be in this second position or it can be in the very last position, but it cannot be something like this. This would automatically disqualify this as being REF or REF because it's not to the right. So that has to hold for RREF and REF. And then finally, for RREF, every pivot needs to be a 1. So like, no threes, no sixes. Every pivot needs to be a 1. Your first non-zero entry in a row needs to be a 1. And there needs to be zeros above and below every pivot. So what I mean by that is like this matrix is obviously the identity matrix, and this is obviously RREF because as you can see for this middle term, there is a 0 up above and there's a 0 below. There are no non-zero numbers above or below. That being said, let's take a look at our options. Number 1, E naught, which is this matrix, is row echelon form of A. This is not true because it violates rule 2. We have this pivot 1, but it doesn't start directly to the right of the prior pivot. This is the prior pivot we have. This 1 needs to be here for us to consider E naught in REF form. So 1 is not true. E naught and E1 are these two. This one is actually true. As you can see, all zeros are at the bottom, and the pivot starts to the right of the first pivot. So 2 is actually true. E naught is the reduced row echelon form of A. So RREF, all zeros are at the bottom. The pivot in the next row starts to the right of the first pivot. Yes, there's the pivot 1, here's our pivot 2, and it starts to the right. Every pivot is 1. Yep. And there are zeros above and below every pivot. So there's zeros here, 0 here, 0 here. So 3 is also true. 4. E naught is this and E1 is this, and the statement is claiming that they're both reduced row echelon forms. This is actually not true. Why is this not true? If you look at E1, this is our pivot in row 2, but there's not a 0 above this. There's a -6, right? That can't be true. So this is now false. So our answer comes out to be 2 and 3 are true. So C. All right, number 10. Number 10 it's a pretty standard linear problem. It really tests your knowledge of these systems of linear equations, and we will be using two concepts here. We're going to use a little bit of row reduction, and we're also going to use a little bit of determinants. So let me put this into matrix form, which obviously you just take your coefficients and you augment your, right-hand side. This is a K, this is a 1, this is a 3, 2, 6, 7, B. Right, so this is what our matrix looks like. I'm going to start by saying, doing something like row 3 is equal to 2, or row 3 is equal to row 3 minus 2 times row 1. This will put zeros where our 2 and 6s are. So our new matrix looks like this. So 2 minus 2 is 0, 6 minus 6 is 0, 7 minus 2 is 5, and B minus 2 is B minus 2. So this is another matrix that we have going for us. Something else I will do, row 2 equals row 2 minus 3, row 1. I really just want to get rid of this 3 in the first column, second row. So now we have 1, 3, 1, 1. 3 minus 3 is 0. This is K minus 9. 1 minus 3 is -2. 3 minus 3 is also 0. Now you have 0, 0, 5, B minus 2. And now finally, I do want some kind of relationship between my Ks and Bs in the same row. So to make that nice and easy, I'm going to say row 3 equals row 3 minus row 2. Yeah. So now 1, 3, 1, 1, 0, K minus 9, -2, 0. 0, this turns into a 9 minus k, this turns into a 7, this turns into a 2 minus b. Now I'm going to rewrite this matrix in equation form. So we have x plus 3y plus z equals 1, k minus 9y minus 2z equals 0, and 9 minus k y plus 7z equals 2 minus. Right, so these are our equations. So now let's go through our, um, you know, our statements one by one, right? So the system will have only one solution for any values of k and b. It might be a little tricky to see when this is true or not. But let's say, for example, k is 9, right? Because it says any values of k. So when k is 9, our matrix looks something like this. This is our matrix, right? Because we ignore the augmented side for now. Because what I'm trying to do is I'm trying to take a determinant right now. If you look closely, when you try to take this determinant, because you use your method of like, you go like so, and then you're like, oh, 1 times your matrix of 0, -2, 0, 7. If you ever have two 0 entries in a 2 by 2 matrix and you're trying to find the determinant of that, it'll always be 0. And when you take a closer look, that's actually always the case. So this determinant is always going to be 0. So when k is 9, the determinant is 0. And what do we know when the determinant is 0? That means there is no solution to our system. So one is inherently false. 2, if k is 9 and b is 3, the system will have no solution. Let's see if that's true. We're going to plug in 9 and 3 into our system here. So we have x plus 3y plus z equals 1. When k is 9, our y's go away, right? -2z equals 0. And 7z is equal to 2 minus b. 2 minus 3 is -1. Well, here z is 0, but here z is not equal to 0, right? So therefore, we're obviously contradicting ourselves, and 2 is also false. When k is 9 and b is 3. No, sorry, I'm saying there is no solution. So 2 is true. This says no solutions when k is 9 and b is 3. So yes, 2 is true. If k is 9 and b is 2, the system will have infinitely many solutions. Let's see. If k is 9, so again, we have x plus y plus z. I'll label this. This can be statement 2. This is statement 3. This is statement 1. Equals 1. Again, when k is 9, this just goes to 0. So -2z equals 0. And 7z is also equal to 0. And now you have z is always going to be equal to 0, right? Because now that's nice and consistent. So then you're left with this equation of x plus y equals 1. So as long as x is equal to 1 minus y and z is equal to 0, there will always be some solution, right? Y can be anything as long as it's equal to, or x can be anything as long as it's equal to 1 minus y. Therefore, 3 is also true. Now let's look at 4. If k is equal to 7, this system will have only one solution for any value of b. So this is our final statement here. K is equal to 7. x plus 3y plus z equals 1. We get minus 2y minus 2y minus 2z equal to 0, which is the same thing as saying y is equal to z, y is equal to minus z. And now you have k is equal to 7. So 2y plus 7z is equal to 2 minus b. Right. But we know y is equal to z, so we can just say, or y is equal to minus z, right? So we can just say minus 2z plus 7z is equal to 2 minus b, which ends up giving us 5z is equal to 2 minus b. Just by looking at this, you can see for any value of b, you will have some value of z. You negate that, that gives you your value of y, and then you can just solve for x. So therefore, you will only have one solution. It just depends on what you set your b value as. So 4 is also true. This gives us E as our answer. All right, moving on to 11. We're giving matrices A and B. B is actually not given to us, and C is also not given to us. We're given that AB is equal to 1, 3, 5, 2. We're given that CA is equal to 1, 3, 5, 2. We are also given the matrix that is the inverse of A, and we want to find B12 and C12. All right, very well. So I will rewrite this as this is actually a very nice question. AB is equal to CA, which is equal to 1352. Right there. Yeah. So I can say if AB is equal to 1352, then one very key identity that I want everyone to know is A multiplied by A inverse is going to give you, which is your identity matrix. And I times literally any matrix is just going to give you that matrix. What do we notice here? If I multiply by A inverse on the left side of this equation right here, I get A inverse times AB. This is actually equal to, this is actually just equal to B. Right, because because when we multiply matrices, we go left to right. A inverse times A is I times B is just B. Right. So all we have to do is multiply those matrices together. So, and we know what AB is. We know what A inverse is. 1 minus 3, negative 1, 4 times AB, which is 1, 3, 5, 2. Now, we want to find B. We want to find B12. Right. So, and that's in our first row, second column. First row, second column. B12 is equal to 1 times 3 plus negative 3 times 2. 3 minus 6 is equal to negative 3. So B12 is negative 3. Just off the bat, we can cross these two out. We're going to do the exact same thing for CA, except we're going to say CA, we're going to multiply A inverse on the right side. Because, again, we're just multiplying things together. A times A inverse is I. CI is going to be C. Right, we know what CA is. What is CA? CA is also 1, 3, 5, 2. What is A inverse? 1, negative 3, negative 1, 4. We want to find element C2. C12. What is C12? That's first row, second column. First row, second column. which gives us 1 times -3 plus 3 times 4 is equal to 9. Therefore, your answer here is okay. So that was the end of exam 1 from fall of 2022 from MA 262. I hope this video was helpful, and good luck studying.